Okay, yeah, welcome everybody to this talk on SIM. It's actually not so much on SIM in this case. It's some more general thoughts on super resolution microscopy, but of course SIM is one of them, and that's why I want to talk about these various aspects of super resolution microscopy. So this is the overview. I'm first going to introduce resolution limits and then try to motivate why I'm a big fan of Abbe's resolution limit. Then I'm going to show you the categories that that various super resolution microscopy methods can be sort of grouped into, and in the end say a few things about what might happen to structural illumination in the future. So you might have heard of Rayleigh's limit. So the Rayleigh limit is introduced by Sir Rayleigh. I don't know if he was actually a Royal Society fellow. I would guess he was. And his idea was to say, okay, I can resolve two point-like objects when their images are in such a distance that one of the object falls into the position of the first zero of the second object. And so that's the Rayleigh resolution limit. And there's another one, which you can say another famous Englishman, Airy. And so the Airy unit is often used, for example, in confocal microscopy, and it's based on the distance on the diameter of the Airy disk. And the Airy disk is this middle part of the point spread function. So this part from the 0 to the Rayleigh limit. And then somebody else came up with the Sparrow limit here, which is placing the 2 points at such a distance that there is no dip in between. So you see here at the Rayleigh limit, we still have a significant decrease in intensity, so that normal people would probably say, well, they are still easily separated. But at the Sparrow limit, this dip has vanished completely, or just about has vanished. And of course, the most commonly used resolution limit is the full width half max of a single point emitter point spread function. So that means the image of a single point emitter will give you such a sort of cut through. And if you then determine the full width, this width at half the maximum of the intensity, then you get the FWHM, so the full width half max. So I'm trying to argue that all of these resolution limits are kind of easy to understand, and they might be useful in their context, but they have lots of problems when it comes to generalizing them as a measure for resolution of a system. So what can a system sort of image and what can it not image? To this question, they are really not that well suited. And to make that point, I want to give you a few examples. So for example, if you modify the backfocal plane of your microscope. So this is an ordinary transmissive backfocal plane of the microscope, and we would get a full width half maximum, for example, predicted to be about 0.52 lambda over NA. So you can get that. But now I'm going to make a super resolution microscope. And of course, since we're talking about SIM, I invent the SIM detection microscope. How does it work? Well, I put an aperture in the backfocal plane. So my pupil now, instead of transmitting everything, just transmits two tiny little dots, one at the left side and one at the right side of the pupil. So what will happen now to my point spread function? Well, the point spread function will change. And as it turns out, it changes like this. So I have a massively reduced full width half maximum of my point spread function at the expense of some pretty high side lobes. Well, in fact, the point spread function would be, of course, the same function for detection now that SIM would ordinarily have for illumination. So we would be getting a detection point spread function that has a cosinusoidal or sine square, cosine square intensity distribution. And of course, this is utterly useless for any sensible imaging, because our optical transfer function looks like this. So out of the whole spectrum of an object, and an ordinary transfer function would maybe look like this, we now get only these three peaks. So that means we've lost 99% of our sample information. We can only measure a particular frequency and the zero frequency, and that's it. Nevertheless, the full width half max would tell us, oh, it's a great super resolution microscope with a in fact a super resolution capability because it has a significantly smaller full width half max. As you see by the equation, it's actually lambda over 4NA what we get here at the full width half maximum, because it's just half the distance between max to max. And lambda over 4NA is a lot smaller by almost a factor of 2 than 0.52 lambda over NA. So, but again, it's not very useful. So you see the problem is that when you are using these point-like resolution limits, you always have to say, you have to put a little star and then say, but don't do this, and don't do this, and don't do this. And the problem is that this lists of what you should not do becomes actually quite long, because you can always sort of evade the strategy and come up with something new. But in the end, they don't really help you and don't make a better microscope. So here's another example of a much debated way of doing this, which is called Toraldo filters. So Toraldo di Francia has, I think, some time in up with this great idea of having a ring of phase and amplitude modified apertures. So the series of rings. And if you do this modification in the right way, he found out that you can actually create a point spread function that looks pretty much like this. So it has a small central spot, and this spot can be significantly smaller than it normally would be. For example, here it's designed to be 1/3 of an array unit. And the expense that you pay for it is that the side lobes not only go as high as they were in my sim detection point spread function, but actually they go in this case, 1,000-fold about higher than the central lobe. And you can drive this to the extreme, and he sort of proved that you can move these further sideways, and you can make this infinitely small if you just put more ring properties. The problem is only that the side lobes become infinitely high. So the point is that this microscope actually, in terms of its optical transfer function, doesn't help you at all. It doesn't increase the optical transfer function by anything. It just redistributes energy inside. And to create this small full width half max here, or the small array distance, if you want, but it's not very useful if you want to image anything practical. So that's what sense does super resolution microscopy make if we define it only in terms of things like the full width half maximum? And I would say, without this extra star saying you shouldn't do this and you shouldn't do this, it doesn't make much sense. So I'm not advertising for not using this measure. It's quite useful, but it is only useful as long as we all behave basically and say and think in the background, well, not more than 10% side lobes or something like this. Right, so here I've written down a couple of like wish list of figures of merits. So you can say there's different resolution limits, Abbe's limit, the Sparrow limit, Rayleigh, full width half maximum. And I've also written down the Fourier ring correlation here, which is not really a resolution limit, but it's a way that you can sort of plot the resolution capability. And my wish list would start with saying, okay, if we want a resolution limit, we want that there is a clear prediction, a clear answer whether something is resolved, yes or not. And it shouldn't be like almost resolved or something like this. It's nice if you have a clear-cut answer that something is resolved. And so that's the case with Abbe, Sparrow, and Rayleigh, but not really with the FRC because it's just a curve. Then should you, well, it would be nice if you can somehow predict what happens if you do superpositions. And the problem is with all of these other limits, like the point limits, well, you can of course write your object as a superposition of point emitters. However, these definitions of Rayleigh limit or full width half max or something like this, they don't help you to predict what features in the object you can in the end observe or not. It really then depends a lot on the object and how would you define the full width half max of a line. Okay, that might make sense, but then how is it related to the one of points? It isn't really that directly. It depends on the shape of the point spread function again. So you cannot derive a clear-cut prediction only from this information. And that's different for Abbe and in a way also for the Fourier ring correlation. And ideally, I would like a resolution limit to be something theoretical that does not depend on your actual realization of the instrument. So for example, I don't like limits where you say, if I expose double as long, I have a better signal to noise, and then I can resolve something, because then it's not about the instrument you're building, it's about the experiment you're performing, whether you can resolve something or not. And it's also always a sort of a weak definition, because it also depends, like I say here, on the sample size and not only the signal to noise. For example, if it's a very periodic sample, by making the size bigger, you might be able to then realize that there is a certain periodicity in the data which you couldn't before. And it is nice also if there's no, I call it pathological way to beat it, and that would be just modifying some pupil plane filters. And that is also the case for the upper limit. You can do whatever you like to your pupil plane. You're not going to change the upper limit. I mean, except making it smaller, worse if you're blocking some part of the pupil. And finally, it should be easy to understand, and that's the biggest problem with the upper limit, because the upper limit, in a way also the Rayleigh limit and the Fourier ring correlation, are kind of hard to understand. And that's, of course, I think the main reason why full width half max and the sparrow limit are used, because they are kind of really easy to grasp when it comes to imaging point objects. And they are very useful also for characterization, because you can make objects that are point objects. Right, so I've mentioned the upper limit a lot, but I haven't explained it so far. And so this next little part is about what is the upper limit actually. And of course, we are dealing with light, and light is normally, a model for light is basically to picture it as a wave, or as an electromagnetic field that has a wave nature. And how do waves behave? Well, if we send, for example, a plane wave through a point, a pinhole, then we get a spherical wave emanating from that pinhole. And now what Ernst Abbe realized is that if you have not only one such pinhole, but instead have an object that has a very periodic nature, then you get these interesting phenomena of diffraction or diffractive orders. And as you can see in this little animation here, there seem to be some sort of region where there's some overlap of all of this stuff. But then when you propagate far enough, you see that you have a beam that goes straight on, and a beam at an angle, and another one at a negative angle. And of course, this is the zero diffraction order, so the directly transmitted light. And this is the first diffraction order and the minus first diffraction order. And now Ernst Abbe realized if you want to form an image of that structure here, what you need to do is you somehow need to capture these orders and make them interfere again, so that they can, via their interference, recreate an image of that structure. And if you want to formalize it, it matters what the relative optical path differences are between these various slits here and the direction in which you're propagating your light. So more precisely, this is shown here. If we imagine our wave comes from the left side and hits our periodic object, we have the first diffraction order. And this first diffraction order is captured by the objective and ultimately has to make it through this objective. And this is indicated by this back focal plane aperture. And that's what we always relate things to. So this is the pupil plane. That's the diameter of our pupil. And then the light interferes in our image plane. And if you now do the math, you see that this distance here has to be lambda. And why did I write lambda over n? Because if we are doing immersion microscopy, then we place this whole thing in an immersion oil, and therefore the wavelengths become smaller in that medium. And so this is really just the wavelengths in the medium. And so you see that difference is now d times the sine of this opening angle, which is this angle here, is lambda over n. And if you write that down here, then you're surprised, because that's not the famous equation that you know. So what is wrong? Well, there's nothing wrong. And actually this equation you find in Abbe's famous paper, which actually he also wrote a letter to the Royal Microscopy Society, where he's put some of his thoughts down. And also this famous equation that is shown everywhere, I think that is from his handwriting in this letter. And so what, of course, he was a smart guy. So what he thought is, well, if we want a better resolution, what about sending in our illumination beam obliquely to our sample? So if we do so, then the zero diffraction order, the directly transmitted light, goes onto one, or passes in one side of the aperture, whereas the first diffraction order passes on the other side of the aperture. And what you now need to do is you need to consider this red path, which is now going first from here on an angle to this grating-like structure and then to the other side. And this gives us this factor of 2 in the end. So it's like 2D if you want. And so this is then Abbe's equation. And in Jena, we have a nice memorial. Actually, I've seen just the other day that it was freshly cleaned now. So this is still an older picture. And his handwriting is engraved in this memorial, as you see here. And what does it really mean? Well, D is the minimal grating constant. So that's the pitch between, or the pitch of the grating, that's the smallest pitch of a grating that can still make it through our system. And that is related to the wavelength of light together with the refractive index. So that they from the wavelengths of light in the medium, and then 2 times sine alpha. And typically this is summarized differently, and this term n sine alpha is called the numerical aperture. You would say lambda over 2 numerical aperture. Well, now you might say, what has this all to do with fluorescence imaging? Because in fluorescence, we are not sending light through a scattering medium and then looking what we can resolve. Now we are interested to resolve structures that are fluorescing, and they irradiate light by themselves, seemingly, almost like a lamp at home or something, a thermally emitter. But in this case, they are, of course, excited by light, but they completely forget about the phase of the light they were excited with, and therefore they look like self-luminescent objects to us. So the point is that in this case, we can do a different approximation, which is that the microscope image is to a very good degree, it's actually described as a superposition of these individual emitters. So that means we can just convolve our object with the point spread function as it's shown here. So we have this object and we have a point spread function. It is as a painter paints with a brush. We just take the point spread function and as the brush and then paint the object. Actually, it turns out you can also inverse this. You can also say, this is my object and this is my point spread function. You get the same result, just a side remark. And of course, to make a smaller point spread function is the whole trick of super resolution microscopy, because then we get sharper images. So how does that relate now to Abbe's picture? And it turns out that, if you want, by mere coincidence, the same 2 rays that Abbe was considering that make it through the edges of the aperture, they are responsible for defining the highest spatial frequency features, so the highest constituent periodic signal in the point spread function. And as it turns out, this is then responsible for also the resolution limit that this microscope can transfer from an object, a self-luminescent object, a fluorescent object, to the image plane. And you see here on the left, the black dots are sort of our fluorescent grating, if you want, and this is the image of the fluorescent thing. And to be able to form such an image, we still need to interfere these two beams. Otherwise, everything is blurred together in such a way that there will be just a homogeneous thing instead of a grating. And this is nicely summarized in Fourier space by plotting this optical transfer function, or also sometimes called modulation transfer function, which is really just the absolute value of the optical transfer function. And this convolution operation that you've seen as this complicated drawing with the brush operation in real space, in Fourier space, becomes really, really simple. It's a simple multiplication. And therefore, the name optical transfer function, because this function tells you the higher the spatial frequency of the grating, that means the finer the grating constants are, the less good is the transfer. And eventually this contrast not only approaches 0, but it actually reaches precisely 0 at a certain limit. And that happens to be exactly the Abbe limit, only this time in Fourier space. So 1 over the grating constant, or depending on how you define it, 2 pi over the grating constant. And so this fixed limit means that nothing is transferred for higher spatial frequencies. And that's the good thing, because the upper limit is really a yes or no answer. Are you below the upper limit? Then there's a chance to image something if the signal to noise is good enough. And if you're above the upper limit with your object, there's no chance. You can do whatever you like. The image is indistinguishable from just a constant background. So there's no chance to actually resolve that. So that's the big bonus of the upper limit, that it has a nice yes or no. You can actually decompose anything into periodic features, and therefore you can actually describe very simple from this upper limit what part of your image information makes it into your image plane. So unfortunately, now coming back to SIM, there's a misunderstanding, which is that you could use SIM, for example, to get super resolution when you're dealing with transmission microscopy. It turns out, no, you can't, because ABBE already considered the maximally oblique illumination angle, and that's the best you can do there. If you really write it down for any illumination angle, and if you had a holographic detection method, then this would be the equation to use. So there's lambda, instead of lambda over 2NA, it would be lambda over the NA of excitation plus the NA of emission. But if you're using the same objective lens, then this is lambda over 2NA. And you could now illuminate, for example, if you think about structural illumination, instead of coming from one side and from the second side simultaneously to create some sort of intensity structure, you could just illuminate from one side and then sequentially from another side. And it turns out that the resolution capabilities in terms of upper limit are exactly identical to this. And there's basically no benefit if you do this at the same time. Having said that, there might be reasons to do it. So if you want to disentangle phase information, there might be some reasons that you want to do it in such a structured illumination geometry, but it's not an excuse to do it for super resolution, because you're not going to get any super resolution. And unfortunately, there's a lot of misunderstanding there, and people claim super resolution in sort of scattering-like geometries, which is really not existing. And yeah, when you measure it, then there's some misunderstanding.
Rainer, you are muted all of a sudden. Yeah.
I saw you just muted me.
No, I didn't.
Well, it said the host just muted you. So
it
okay.
Must be Irene.
Okay.
Sorry for
Sorry,
that.
I was just trying to mute the participants.
It's okay, no problem. Okay, but I think you still got the point here with this slide, right? Kitty? Well,
yeah.
I think that was not muted. Good.
Yeah.
So what's the time saying? Oh, okay.
You have about 15 minutes, Rainer.
Yeah. So now let's go beyond Abbe's limit. So what can we do? Well, as I said, fluorescence is different than scattering. So what about if we now combine excitation and emission here? So how can we do that? Well, in fluorescence, we have this extra degree of freedom to play with our illumination, because a fluorophore can only fluoresce when it is illuminated with locally bright light, and it does not fluoresce if it feels locally dim light. You might say now, well, that should be the same with scattering. You're not scattering if there's no light. Well, that's sort of right, but you can also treat scattering as just saying each of these two waves would scatter, and then the result is simply what you get when you have when you sum up the amplitudes that you would measure with each of the scattering, and then you would see that there seems to be no scattering because they would destructively interfere. And you cannot do the same with fluorescence. You really have to go for intensity. So speaking in quantum mechanical terms, a fluorophore, you can imagine that it does a measurement, right? It is already a detector. It detects intensity, and then it re-emits some light. And this re-emitted light it bears no phase relationship to the incoming light. Not even the color is the same, in fact. Right, so, well, what does that mean? It turns out, well, here's a little example of how SIM works, and that's all I'm going to show about SIM because I'm sure other people will cover it much more in detail. So if you have a sample that has a high frequency that you can normally not image, that means in your microscope it would look like this. But then what you can now do is you can sort of information by, instead of imaging it directly, you first illuminate it with another very high frequency grid that you generate by interfering laser beams, for example. What you then get is this interesting effect called the Moire effect, and you see these very low frequency fringes here. And these low frequency fringes you can, of course, observe without problems with your microscope. So they would look roughly like this. And now the trick is in structured illumination that you can use that measured information together with the prior knowledge, if you want, that you illuminate it with a particular grating of a particular grating constant. And then you can reconstruct a SIM image from that, and you can recover the high frequency structure that the sample really had. And so that's in a nutshell what SIM does. Of course, in practice, it's much more difficult because you have to figure out some of the parameters from your images, like the grating constant, the grating phase, and things like this. But this is all details, but the principle is like this. So what you get then is this typical resolution improvement, for example, from a wide field image of an actin filamentous network here to a structured illumination image where you can clearly see the resolution gain that you have. And this idea is what we described in 1999 in this paper here, where we imaged beads, and you see the resolution improvement on the left side, and at the same time you see how Fourier space increased its sort of extended its support, so you have a higher upper limit. And here's the picture from that paper that shows you how the interference of the beams sort of leads to an enhanced lateral resolution. So the question is, does structured illumination really circumvent the upper limit? Well, I would say yes, it does, because you're combining excitation and emission, and that basically shifts the upper limit of an emission-only fluorescence system, or in fact being identical to a transmission-only system with oblique illumination. It essentially doubles it because of the influence of excitation. So that's great. But on the other hand, that's nothing special, because so does confocal microscopy. If you just have a confocal microscope, you're illuminating with focused light, and you image, well, if you take, for example, an image scanning microscope, you would even take an image at every single point position, or in a confocal microscope, if you have a small pinhole, you actually do get a resolution improvement, and the upper limit is the same as for structured illumination. Nevertheless, there are differences between. So how is it possible, again, to stress the fact so that the enabling bit of this whole discussion is really the independence between excitation and emission, so the loss of phase information. So I call it here the phase randomization is really the trick that buys you the resolution improvement. So, but then why is structured illumination better in some sense than confocal microscopy? Well, of course, the devil's in the detail. And so the question is, how can we show this? And so in what sense is SIM better than confocal? And I think one good way to show this is by plotting something like a transfer function. And this is, as you will see, wait. No, sorry. First of all, so yeah, what are the technical differences if you boil it down like this? So for SIM, for structured illumination that is really geared towards high resolution structured illumination, there's two essential tricks that you use. One trick is the high frequency illumination. That means you're trying to push the illumination grid to the highest possible frequency that you can. And that is typically limited by the numerical aperture of the illumination objective if you want to illuminate through it, or you can go from the sides by having two opposing beams if you want, or you can go even in turf where you can increase the refractive index of the medium that generates the beams so that you can get even smaller. But that's basically it. But the cool thing there, and that's maybe the thing to understand, is that you are not limited by the strength of the transfer function, because these beams, these two laser beams, for example, they are coherently interfering. And if if you care for their polarization and things like that, you can get 100% contrast at the highest spatial frequency. So even though the normally incoherent transfer function would sort of decay in a triangular fashion to almost zero at these frequencies, we can still pump in very much energy, if you want, into these really, really high frequencies, and we can have them at 50% of the strength of the middle peak. So that means they have 100% contrast in terms of the sinusoidal wave that you have. And so that's one big trick. And confocal microscopy doesn't do that. It gets in the whole aperture, it is limited to the same transfer function as the incoherent transfer function. So it has very, very little high frequency information out there. The limit is still the same, but it's not very, very prominent there. And the second thing, the second thing is what I put on the top here is the weighted averaging. So once you have that information, in SIM, you're separating the orders and you're then moving them into place, but you're not just summing them up as, for example, any sort of Nipkow disk microscope would automatically do. So in a way, you can say a Nipkow disk microscope is a SIM microscope with all-in hardware without needing a software. But that's true, but it's not as good as SIM because it simply sums them up rather than doing a proper weighted averaging to enhance the signal to noise. And the same is true for some other system and some early publications. But another issue is the generation, as I said, with SIM is really 100% contrast, and some other systems that are based on incoherently generating these images, for example, by scanning the beams to generate the SIM pattern, that all works, but just not as well as a proper system because it doesn't have this high contrast. Yeah, and so as I said, yeah, many systems like the original publication by Lukosz and Peter So and so on, they did not have this weighted averaging in them, so they don't quite perform as well for the high frequency contrast or for the mid-frequency contrast as well as the weighted averaging based systems. And so here's a way that you can measure this performance. I won't go into the detail, but we call this the noise normalized OTF, and it's basically a modification of the transfer function in such a way that you can compare systems because they theoretically all have exactly the same noise. So that means what you're really plotting here is, if you want, is the signal to noise as a function of spatial frequency. And if you do that, you can see that confocal is pretty good with a closed pinhole. For example, for the high frequencies, much better transfer than the open pinhole ones, which is this curve. But you see, for example, that with image scanning microscopy, so what is also called ARRI scan or some other methods that are in that same sort of ballpark, so also the rescan confocal and so on, they have a much better performance than the confocal in this case. But how about SIM? So we go now to structured illumination. One cool thing is that this OTF, the noise normalized OTF, has this great ability that it can also describe the performance of image processing based system like the SIM system in a fair way to compare them to hardware based systems. And so if you have that,
you have 5 minutes.
Yeah, it's okay.
Okay. Yeah.
So if we now compare the SIM system to ISM, you see that for the high frequencies, it really is much better than even the ISM, and of course, much better than the confocal system. So we have orders of magnitude improvement for the very high frequency. But having said that, you also see that such a high performance SIM system is not as good as an ARRI scan or image scanning based system for the mid frequency region. Yeah, so that means it really depends on the biological question, which system you want to use. If you do not need the utmost highest resolution, you're probably better off with such a system, not to talk of the other advantages that it has if you're using point scanning compared to almost wide field like illumination in the SIM system. So then the final bit I want to mention is this beyond the excitation emission combination. So the question is, can you go higher than even this factor of 2 that we discussed, or a little bit more than 2 if you're going with opposing beams? And the trick is, yes, you can by exploiting nonlinear excitation. And so here's some examples that on nonlinear SIM are massively based on some sort of saturation effect. And the saturation introduces a nonlinear dependence of the emitted light on the incoming light. And that is the trick of super resolution. There's another way that you can enhance your resolution. That's exploiting prior knowledge. So that means, for example, single molecule microscopy, you know, every single point you see in your image can be assumed to be a single molecule. Therefore, you can localize it and then you can pin it down to a particular position and you can redraw your image from that. And this is, in my mind, based on the molecular nature of our world. And you're exploiting the fact that, you know, these are molecules. So, and that's sort of, one point I want to make. It's often said that switching is sort of the defining feature in super resolution. And I think really it isn't. So of course, there's no doubt that fluorophores change states, for example, from S0 to S1 state, as you might know. So fluorophore gets excited and then after some vibrational relaxation emits fluorescence. But of course, that's what it does. But is that the defining feature of super resolution? Of course not. So in my mind, the defining features are rather things like exploiting the near field. So that means you have to be really, really close to your dielectric transition from one medium to another. In which case you can use basically some tricks of Maxwell's equation that there's in addition to propagating waves, also non-propagating waves. Then there's another trick is this non-linearity. That means that this linear combination of excitation and emission as it is done in SIM can be circumvented by having a nonlinear response of your fluorophore. If you want to put it in the most general way, you would say you need a nonlinear dependence between the local detection and the local influence. That doesn't even need to be light. It could even be a near field scanning tip or whatever you want, right? It could be a temperature gradient if you want, or something like this that influences it, that gives you super resolution. And the last thing is exploiting prior knowledge. That, of course, is true for any type of sort of deconvolution, but it is also true for things like single molecular microscopy. So, and as you know, that can actually practically get you really, really nice high resolution images. And so to give you a few examples why nonlinear, why it's not the on-off game that really defines the super resolution, but in my mind, it's the nonlinear photo response. So if you think about nonlinear SIM, you have this behavior, and I really have difficulties to imagine what would be different between a normal fluorescent SIM microscope and the saturated SIM microscope in the sense of switching states. So just by introducing the saturation, why have I changed my switching behavior somehow? I think it's not really a defining feature, this switching on-off game of fluorophores. Yes, they do switch and they do things, but we are not really exploiting it, maybe except in the case of single molecule microscopy, but there we use it not for the super resolution, but for making them into single molecules, which is a totally different thing. And the same arguments you can do for STAT and, for example, for pain. So what is the switching in STAT really? Is it the switching from S0 to S1 state? Clearly not, or from S1 to S0. That's not meant. So I think the arguments are more like you're switching between these sort of states of able to emit a photon in the detection band or unable to emit a photon in the detection band. But to me, that sounds relatively artificial definition, because you need to introduce other states which are not physical states. They are more like abilities to do something states and so on. And then in that sense, I don't really understand what's the big benefit to talk about a switching behavior here. And so also in my mind, the real benefit of STAT is the saturation of the stimulated emission. You're driving the system into saturation. And again, the saturation is the nonlinear dependence of emission on illumination that you put there. And for paint, it's a prior knowledge that you're observing single molecules. Yeah, you could say, okay, it's a switching of a bound to an unbound state of a molecule, but that's a totally different thing than photophysics and so on. Right. And here's another third example, which is Rabi oscillations that you could also exploit. I just put that down there because, interestingly, in the very first, in the SIM patent, we have this Rabi oscillations in there, but there's also some more recent article where they use this. And so the trick is here, you really don't have states anymore, because the point of a Rabi oscillation is that Rabi oscillations do not, the molecules are not in a particular well-defined state. They are in two states at the same time, and they oscillate based on how long you have this superposition of the two states. Right. So with that, I'm pretty much almost at the end. So what I want to just put here is a little graph that shows you these various ways that you can have super resolution in a graph. So I think this sort of pictures roughly what you have. So you have an increase from low resolution by just emission imaging to having this excitation emission combination. So this is the world where SIM lives in. And then you have nonlinear combinations, which is like STAT, SAX, and nonlinear SIM. And then you exploit prior knowledge, like single molecule nature, which gives you all the way from modest improvements in deconvolution to the top resolution instruments like single molecule localization or MinFlux. Good. Time is over, I guess. With the future, I have only one slide here, which says, I think this is what is going to happen. I will quickly say thank you to the people of my group. So summarize my talk. There's more than switching, and there's still room for super resolution and improvements in the future. And I hope you all enjoyed the great conference. Thank you very much to all the members of my group. And this is some of them that contributed over the years, more relatively recent one. And I will just end my talk and go back to the slide with the future thing, so you can look at it while you're asking questions.
Yeah, thanks, Rainer. Excellent talk. A lot of important points made. You will also have time during the panel discussion. So if you wanted to do your brief history, we can do it there.